Hey Chem Kids, Campbell here, and today we're going to talk about bonds, chemical bonds. In particular, we're going to talk about why do bonds form between elements to form compounds, and what's the difference between them. There's ionic compounds, we're going to have covalent compounds, also called molecules, and we're going to use information on the periodic table for electronegativity to figure out what's what. Well, I guess first we should explain what a bond is. What a bond is a force of attraction between atoms, and they do this so that they can attain stability. Remember in our last unit we talked about the octet rule. The octet rule says that all atoms want 8 valence electrons. They want that outer shell that's just like the noble gases so that they're stable. And if we go back to the chapter before when we did electron configuration, right, we saw that noble gases had this full outer shell, right? A full outer shell is 8 electrons, so that means a full s and a full p orbital. Now, when we have metals like, say, sodium, which is in that very first column on the periodic table, it has that 1 valence electron, right? It has this lonely guy in the outer shell. Well, what does it do to try to be stable, to get that outer shell that's full of electrons? Well, it certainly isn't going to add another electron in the s orbital and then 6 more in the p, right? That would be really hard. So what does it do? Well, it just loses this guy. When it loses this guy, right, then it looks just like neon. So when it does that, it becomes an ion, and it becomes the sodium plus 1 ion, right? It loses 1 electron, and when you lose an electron, you become positive. All right, let's take a look at nonmetals, right, on the other side of the periodic table. Well, here's argon again, a noble gas, with its full outer shell of valence electrons. And if we look at the one right before it on the periodic table, we'll find chlorine. Right? Chlorine is just missing the 1 little electron here. So if it could just get 1, right, it'd just be like argon, and everybody wants to be like argon. So the easiest way to do that is to add an electron. Maybe it takes it from sodium. When it does that, right, now it has this full, beautiful outer shell. It's stable, it's happy. But now it has a -1 charge, right? If you gain an electron, you become negative. Well, now I've got this positively charged sodium out there, and I have this negatively charged chlorine out there. And remember when I talked about ions, I said that when ions are like that, they're like sticky, right? When I rubbed the balloon, I gave it a charge, and then it stuck to my head. So when these atoms get sticky, they end up sticking together, and that's called an ionic bond. So know that an ionic bond, there's a complete transfer of electrons. And when I get that to happen, right, I get these 2 oppositely charged ions, and opposites attract. So they end up sticking together. So in an ionic bond, there's a transfer of electrons that results in an electrostatic attraction between pluses and minuses. Now, this only happens with metals and nonmetals. The metals become positively charged, right, because they're on the left side of the periodic table. They have less electrons in their outer shell. Then the nonmetals, what they're bound to, the ones that become negative, right, they're over here on the far right side of your periodic table. So here's an example of lithium fluoride. Lithium's a metal. It's in that very first column. So it has this 1 lonely electron in its outer shell. So what it's going to do is it's going to give that electron to something like, say, fluorine. Fluorine has 7 electrons in its outer shell. It's so close to 8. So lithium will give the electron to fluorine, and that'll make lithium positive, right? It lost an electron, became positive, and fluorine becomes negatively charged because it gained an electron. And because I've got this positive, negative, they stick together. And that's my electrostatic attraction. So they form an ionic bond. So lithium fluoride, anytime I have a metal and a nonmetal, I have an ionic bond. Now, what about other types of compounds? I mean, does everything donate and get electrons? Well, no, not all elements are strong enough to grab an electron for one or weak enough to lose an electron. So there are some elements that can't do this, and they share electrons, and those are called covalent bonds. So a covalent bond, there's a sharing of electrons. So what type of elements do this? Well, first of all, we call them molecules when they're bound by covalent bonds. Remember, we're doing molecular nomenclature in this unit. molecular nomenclature. Wait! That means they're two nonmetals bound together. So anytime you have two nonmetals bound together, you have a covalent bond. Now, there are two types of covalent bonds, and it's all based on how good the elements are at sharing electrons, because, you know, not everybody is good at sharing. So, of the two types of covalent bonds, there are nonpolar covalent. Nonpolar means that there's equal sharing of electrons. But not everybody's as good at sharing, like my kids on Halloween with their candy. They share with their mother, but not very well. So a polar covalent bond is one where there's unequal sharing of electrons. So here's an example, and these are kind of like representations of electron clouds. And we can see here the electron cloud around fluorine is much bigger than hydrogen. So if we look at the overlap between the orbitals, we can see that fluorine has more of the electron. Same here with hydrogen and iodine. Iodine is a bigger hog. It's not a good sharer. So it takes the electron from hydrogen more often than hydrogen gets it from iodine. This is opposed to our nice, symmetric, even, equally distributed nonpolar covalent molecules, which anytime a molecule is bound to itself, right, you'd share with yourself pretty well, wouldn't you? You're like, what? So let's talk about this a little more. All right, so it's all about the electron cloud, right? And remember, the electron cloud is where the probability of the electron is going to be. So in a nonpolar covalent bond, I have this nice, symmetrical, even distribution of an electron cloud, which means that the electron is could be found easily here with this hydrogen, or maybe this hydrogen, or somewhere in between. So it's very symmetric because it could be anywhere. They share equally. But in a polar covalent, we have an uneven distribution. So you can not really see the rest of the chlorine here. It's behind my picture. But there we go. You can see that the chlorine here has the bigger electron cloud, so it's an uneven distribution. So it's more likely that you're going to find the electron by the chlorine. So that's a polar covalent bond. Now, how do you know where it's going to be? Well, it's going to be by the more electronegative atom. So remember electronegativity? The values are here on your periodic table in that top corner. Well, electronegativity, remember, tells you the affinity that that atom has for electrons, how much it likes electrons. And so chlorine, if we look at chlorine and hydrogen on the periodic table, right, hydrogen's electronegativity is 2.1 and chlorine is 3.0. So chlorine likes electrons better than hydrogen, so it's going to hog it more often. Now, we actually have a name for these type of molecules. They're actually called dipoles. Two poles. Interesting. Why do we call them dipoles? Well, if we take a look, again, here's our hydrogen and chlorine, and I put the electronegativities up here. There's the ones that you find on the periodic table. And so this is kind of what the representation would look like. What happens is that chlorine hogs the electron. It pulls harder on it. It likes it better than hydrogen does. So maybe it's getting the Tootsie Rolls because hydrogen doesn't like Tootsie Rolls. Well, we get this partial charge separation, and this weird looking Greek letter delta here, plus, means that there's a partial charge on the atom. So it's not a complete positive charge, it's only partially sticky. And this delta negative here means that there's a partial negative charge on chlorine. So how do you know the type of bond? How do you know? Is it ionic? Is it covalent? Is it polar or nonpolar? Well, we do this by, one, looking at what are the atoms in the bond. Are they metals, nonmetals, both nonmetals? We also look at electronegativity difference. So difference being the subtraction. So you go to the periodic table and you find the two atoms that are in the bond, and then you subtract their numbers. Now, electronegativity difference can't be negative, so an absolute value of the electronegativity, or always the higher one minus the lower one, you know. But periodic table, again. So get out your periodic table. All right, so let's take a look at how we figure out what's ionically bound to each other. So remember, an ionic bond is a complete transfer of an electron. So one way we can do that is by looking to see, is it a metal with a nonmetal or a metal with a polyatomic ion? Those are ionic bonds. Or an electronegativity difference greater than 1.7, usually. Definitely if it's over 2. So if I go and I find the two atoms in the bond and I subtract them and the number is greater than 2, it's definitely ionic. But usually over 1.7. But I'm going to talk about that a little later. In a covalent bond, if it's polar covalent, right, we have that unequal sharing and that partial charge separation. This polar covalent bonds always occur between two nonmetals, and I know that it's polar versus nonpolar if the electronegativity difference between the atoms on the periodic table is between 0.5 and 1.7. But like I said, sometimes that 1.7 to 2 is a little fuzzy gray area, and I'll talk about that later. But if it's greater than 0.5, polar. Our nonpolar is when we have that equal sharing, and equal sharing, again, if it's covalent, it's two nonmetals, and the electronegativity difference on the periodic table is going to be less than 0.5. So if it's less than 0.5, nonpolar, equal sharing, no electron hogs. All right, let's do some practice. So here's our periodic table, and I have sodium chloride, hydrochloric acid, and chlorine, 2 chlorine molecules. What type of bonds are these? But let's look up their electronegativity differences and find out. So chlorine, right, is over here, it's 3.0. Sodium is over here, 0.9. So if I subtract 0.9 from 3.0, I get 2.1. Now that's definitely above 2, which definitely makes that ionic. Here we have hydrogen and chlorine together. Again, chlorine is 3.0, hydrogen is 2.1. So if I subtract 2.1 from 3.0, I get 0.9. This is polar covalent, right? It's above 0.5 and it's less than 1.7. So polar covalent. And here, of course, is chlorine. Chlorine is 3 minus 3 is 0. So definitely nonpolar covalent. All right, you try. Pause the video and see if you can rank these bonds from being least polar to most polar. So look up the electronegativity difference of each atom, find their differences, and then rank them. Well, if you did this right, you should find that sodium chloride, right, has that electronegativity difference of 2.1. Chlorine minus fluorine, right, fluorine is 4.0, chlorine is 3.0, so that difference is 1. And then we have oxygen minus hydrogen, and when you subtract those, you should get 1.4. So now we just got to rank them from smallest to biggest. So if you put chlorine, fluorine, less than HO, less than NaCl, you are correct. Okay, last thing, what do we do if there's multiple elements, like say 2 hydrogens with an oxygen? Well, only subtract 1 hydrogen from the oxygen. So don't be multiplying by 2. So look up oxygen on the periodic table, it's 35. Hydrogen is 2.1, and then just subtract those. So don't be multiplying anything or adding anything, just the individual elements themselves. So 1.4, this would be a polar covalent bond, right? Two nonmetals together and above 0.5. Now, what about this whole weird 1.7 to 2.0 range? Well, you have to then look at the elements in the bond. If we look at hydrofluoric acid here, we look at fluorine and it's 4.0 and hydrogen is 2.1. So my difference is 1.9, which is greater than 1.7. But if we look at the two things in the bond, hydrogen and fluorine are both nonmetals. So that means this has to be polar covalent, even though it exceeds that 1.7 cutoff. Or if we look at something like sodium bromide, bromine is 2.8 minus sodium, which is 0.9. That's also 1.9. But sodium is a metal and bromine's a nonmetal. So that makes it ionic. So when you're in that weird range, look and see what it's bound to. All right, do some practice in your packet, and I'll see you in class.